Okay, so let's take a very quick look at something I call quantum thermodynamics. We'll see why in just a second. This is the inhomogeneous Helmholtz equation. Normally, this I have a function here of x, y, z, and t here times this. If this was just some constant or gone, this would just be the regular Helmholtz equation. But because we have some function times the solution we're looking for, it's called the inhomogeneous Helmholtz equation. Okay, let's take a look really quickly at the heat equation or the diffusion equation. By the way, of course, this is negative 2a del squared psi plus some function of x, y, z, and t times psi equals 0. This is, we'll just make some arbitrary constant a, del squared psi plus some another arbitrary constant b, the partial of psi with respect to t. We'll add these two equations and we'll get this equation right here, which is negative a del squared psi plus f of the four variables psi plus b partial of psi with respect to t. Let's let a equal a h bar squared, Planck's constant, reduced constant squared, divided by 2 times mass of the particle, usually an electron, and b equal I h bar. And if we plug that into here and this into here, I'm sorry, this into here, b, we'll get this equation, which of course we can immediately recognize as the Schrodinger's equation. I've changed the f into a potential function of position vector, including time. So we get negative h bar squared over 2m del squared psi plus some potential function times as a function of time and space, and psi equals I h bar partial of psi with respect to t, which is Schrodinger's equation. So we see that Schrodinger's equation has its origins in the fusion of the heat equation and the Helmholtz equation, and it's interesting because. Of course, Planck started the quantum revolution with his black body thermodynamic experiment. Okay, I hope you enjoyed this video.